In 1.8, we are going to introduce what they call the squeeze theorem. It's also called the sandwich theorem, although we'll call it the squeeze theorem. Okay, so it says if g of x is less than or equal to f of x is less than or equal to h of x, and the limit as x approaches a of g of x equals L, and the limit as x approaches a of h of x equals L, then it must be true that limit as x approaches a of f of x also equals L. So let me just sketch what they're talking about and why this works. Okay, so g of x is less than or equal to f. So g of x is low. Let's call this g. Let's see, f of x, g of x is less than f of x. So f of x is somewhere up here. I don't know where it is. Let's call this f. And then h of x is the highest. So h of x is somewhere up here. Okay, so this is saying g of x is less than or equal to f of x is less than or equal to h of x. So g is lower than f is lower than, which is lower than h. Okay, now, if at some point A, let me make this a graph. Say this is the point A. The limit as x approaches a of g of x equals something. Maybe it's 2. If the limit of x approaches a of h of x, this one up here, also equal to, if this and this were equal to the same thing, then it must be true the limit as x approaches a of f of x also equals that value. If you think about that, if this is lower or equal to this, and this is stuck in the middle, if these are the same, then it must be true, then this is also the same because it's stuck in the middle. And you can kind of tell why this is called the sandwich theorem, where this is the bread, there's the meat, or the cheese if you like cheese. Okay, now when do we use this? Sometimes you can create a situation to use it, and sometimes I'll ask you to prove whether it's possible to use this function. Okay, so for example 1, we're going to find the limit as x approaches 0 of x squared times cosine of 1 over x squared, which I wouldn't normally do because this is saying the cosine of 1 over 0, which is cosine of undefined, which I don't even know what to do with that. Okay, so first I need to figure out a scenario where g of x is less than or equal to f of x is less than or equal to h of x. So I'm going to look at cosine to start with. Now I don't know what the cosine of 1 over x squared is, but I know that the range of cosine is always -1 to 1. So even though I don't know what cosine equals to, I know that it must be true that -1 is less than or equal to the cosine of 1 over x squared, which is less than or equal to 1, because cosine is always between -1 and 1. Okay, now I want to create this function, x squared times cosine of 1 over x squared. I'm just going to use algebra. I want to make this x squared, so let me times everything by x squared. So now this is -x squared is less than or equal to x squared times the cosine of 1 over x squared. And then if I times the 1 by x squared, I get x squared. Okay, this should be true. I just followed algebra. X squared is a positive value, so I didn't switch to any inequalities or anything like that. Okay, now, if this is less than or equal to this is less than or equal to this, then I'm going to try to find the limit of each of these at 0. So the limit as x approaches 0 of -x squared is less than or equal to the limit as x approaches 0 of x squared times the cosine of 1 over x squared. And what should be less than or equal to the limit of x as x approaches 0 of x squared? Now the limit as x approaches 0 of -x squared is just 0. That was direct substitution. Okay, now the limit as x approaches 0 of x squared is also 0, because 0 squared is 0. And I don't like that little 2 up there. Okay, so since this limit is 0 is less than or equal to this limit, which is less than or equal to 0, then it must be true the limit as x approaches 0 of that expression is 0 by the squeeze theorem. So where am I going to squeeze this over here? So in conclusion, and to write in conclusion, I'm going to say ... which is like therefore or in conclusion. The limit as x approaches 0 of x squared times the cosine of 1 over x squared equals 0 by the squeeze theorem. Okay, let's look at example 2. Okay, it says let g and h be the functions defined by g of x is -x squared plus 2x minus 3. H of x is 2x plus 1 if f is a function that satisfies g of x is less than or equal to f of x is less than or equal to h of x for all x, what is the limit as x approaches 2 of f of x? So let's try this using the squeeze theorem. Because I know g of x is less than or equal to f of x is less than or equal to h of x, then it should be true the limit as x approaches 2 of g of x is less than or equal to the limit as x approaches 2 of f of x, which is limit less than or equal to the limit as x approaches 2 of h of x. No, I have no information about f of x, but so I'm going to work with g of x and h of x. Okay, let me look at g of x. Limit as x approaches 2 of g of x. I'm just going to use direct substitution. Where is g of x? Up here. Okay, so if I plug in 2, that is negative 4 plus 2 times 2, 4 minus 3. Negative 4 is 0 minus 3, so that's negative 3. So negative 3 is less than or equal to the limit as x approaches 2 of f of x, which is less than or equal to limit as x approaches 2 is h of x. Where's h of x? Right here. So if I plug in 2, direct substitution, that's 4 plus 1. So that's less than or equal to 5. So this is telling me the limit as x approaches 2 of f of x is between negative 3 and 5, but it didn't actually tell me what the limit as x approaches 2 is, because there's infinite number of possibilities there. So in this case, in my conclusion, I'm going to say the limit as x approaches 2 of f of x can't be determined. There's not enough information. I did get an idea that it's between negative 3 and 5, but I don't have a final answer for that. Okay, let's look at example 3. It's very similar. We're going to try that and see if we can get a conclusion using the squeeze theorem again. Okay, so let g and h be the functions defined by g of x equals the cosine of pi over 2 over x plus 2, and h of x equals x squared plus 3. Okay, f is a function that satisfies this inequality. G of x is less than or equal to f of x is less than or equal to h of x. From negative 1 to 5, okay, what's the limit as x approaches 0? Okay, now because 0 is between negative 1 and 5, I can go ahead and try to use the squeeze theorem because there's no discontinuities in the interval at the value I'm trying to test. Okay, so it should be true that the limit as x approaches 0 of g of x is less than or equal to the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of h of x, since the graphs are in that order always at all values, or from negative 1 to 5. Okay, let me plug in, do direct substitution of 0 on the g of x function, which is going to be the cosine of what am I, 0? 0 plus 2. The cosine of 0 is 1, so 1 plus 2 is 3. The limit as x approaches 0 of h of x. Here's h of x. So that's just 0 plus 3, which is 3. So in this case, I can see that the limit as x approaches 0 of f of x has to be less than or equal to 3 and greater or equal to 3, which means that it must be true the limit as x approaches 0 of f of x is in fact 3. So therefore, the limit as x approaches 0 of f of x equals 3 by the squeeze theorem. Okay, last example. Let f, g, and h be the functions defined by f of x equals 1 minus cosine x over 2x, g of x equals x cubed times the sine of 1 over x, and h of x equals x over sine x. For x is not equal to 0. All of the following inequalities are true for x is not equal to 0. State whether each inequality can be used with the squeeze theorem to find the limit of the function as x approaches 0. Okay, just as a note, since we're approaching 0, what actually happens at 0 is irrelevant. Okay, so we're going to try each of these. So the first one says negative 1/2 is less than or equal to f of x is less than or equal to x squared plus 1/2. We're trying to determine if this is, I can use the squeeze theorem as x approaches 0. Okay, so let's see. If I do the limit as x approaches 0 of negative 1/2, that should be less than or equal to the limit as x approaches 0 of f of x. which should be less than or equal to the limit as x approaches 0 of x squared plus 1/2. Okay, now the limit as x approaches 0 of negative 1/2 is negative 1/2. Okay, limit as x approaches 0 of x squared plus 1/2. Well, if I do direct substitution, that would be 0 squared plus 1/2, which would be 1/2. So this helps me determine that negative 1/2 is less than or equal to the limit as x approaches 0 of fx, which is less than or equal to positive 1/2, which is not enough information for me to use the squeeze theorem to determine the actual limit. So in this case, can we use the squeeze theorem? No. Let's go ahead and try the next one. Let's see. If I want the limit as x approaches 0 of this, it should be less than or equal to the limit as x approaches 0 of this, which is the limit as x approaches 0 of this. So let me go ahead and do direct substitution. Okay, the limit as x approaches 0 of negative x to the third is negative 0 is 0. Which should be less than or equal to the limit as x approaches 0 of x to the third. So if I substitute in 0, I get 0. So because the limit as x approaches 0 of g of x is less than or equal to 0 and greater or equal than 0, then it must be true the limit as x approaches 0 of g of x does equal 0 by the squeeze theorem. So can I use the squeeze theorem? Yes, I can use the squeeze theorem to determine that the limit as x approaches 0 of g of x is equal to 0. Okay, one more. Okay, let's try it with this inequality. Okay, the limit as x approaches 0 of this expression, 1 minus 0 squared is 1, which should be less than or equal to the limit as x approaches 0 of h of x, which is less than or equal to the limit as x approaches 0 of x squared plus 1. If I do direct substitution, 0 squared plus 1 is 1. So because the limit as x approaches 0 of h of x is less than or equal to 0 and greater than or equal to 0, it must be true that it actually equals to 0 by the squeeze theorem. So can we use the squeeze theorem? Yes, we can use the squeeze theorem to conclude that the limit as x approaches 0 of h of x is equal to 1.